So, hello everyone, welcome back to Codeverse Coders. It's great seeing you back after about 2 months. So, now let's start with a fresh subject, new lectures. The subject we'll be taking up now, it will be matrix computations. So, let's start. In this subject, we'll be covering different methods, how we can solve matrices, and we'll be understanding matrices from the basic level. You may know matrices, how to solve them, but you have never worked upon the elementary operations. What are the basics? Like you may be applying operations minus, row switching, but understanding that what are elementary operations and what are non-elementary operations, we'll be seeing these basics also. So let's start and delve into this topic. So first, let's start with, I'll be writing some basic operations that we have been doing in matrices. Let's say R3 gives R3 minus R1 plus 3R2. Then we have R3 gives 5 times of R3 itself, and R3 gives R3 minus 5R1. Which of these are elementary operations? So first let's understand what are elementary operations. Elementary operations are operations that work as a one-step operation. One step means associated one column only. Like prime number, understand this is a short trick, like those who can understand them well and good, but you can understand it with the help of prime number example also, like 1 and the number itself. Similarly, elementary operations is the row which you are about to change and another row is used. Like, let's say an example, R2 gives R2 plus 2R1. R2 is the row that we are working on, and R1 is the row we are using to get a required value in your second row. So let's see the first example. We see R3 is the row we are working on, R1 and R2, but here it's a two-step process. So it is not the elementary operation. Next, R3, R3. Is this an elementary operation? Yes, it is. It's a one-step process. So it's a one-step process. Then after that third example, this is also a one-step process like we have seen. So this is also elementary operation. So let's write a generalized definition of elementary operations. So first you have what we can say is row switching. In row switching, we switch Ri and Rj. Then second, we saw row multiplication, where we multiplying by a scalar, like in the second example. Ri gives k of Ri, where k is a non-zero scale. Similarly, you have row addition. Ri gives Ri plus krj. Now, these are the elementary operations. So you may be asking, where is this operation that we used to apply? R3 minus 2R. But here we have a negative sign. So do we have a row subtraction also in elementary operations? The answer is no. The game that is played here is played by the scalar itself. What if I write like this? Has it become your row subtraction? Yes, it is. So that means it is included in your third elementary operation. So next, now let's see how do we construct a elementary matrix. But before that, what is an elementary matrix? Basically, a elementary matrix, it is basically a square matrix denoted by E. It is a square matrix having the property of EA, the product of the result by applying a single elementary operation to A. Now, this would not be clear by just reading the definition. I'll explain it with the help of an example. Let's see the steps on how to create a steps to create a elementary matrix. Here we'll be seeing an example also. So first is choose an identity matrix I of appropriate order that can be pre-multiplied to A. Pre-multiplied to A. So let's say we say case 1 where we say row switching. Now we are saying when we multiply a elementary matrix, let's say identity matrix to any matrix if we multiply, we'll get this matrix itself. So let's say we apply the operation, we interchange R2 and R3. In that case, let's say we have identity as 1 0 0 0 1 0 0 0 1. So when we do the operation, we'll get your elementary matrix as 0 0 1 0 1 0 1 0 0. Have you understood? We just applied the operation here. And another thing is when you take the inverse of this elementary matrix, you get the E itself. E is the elementary matrix. Case 2, scalar or row multiplication. Whenever we have row multiplication case, whenever we are handling any question, work fresh identity matrix so that you can understand better. Let's say we have K here. So our elementary in this case will be I comma I. We'll place K at I comma ith position. Let's say for an example, we take R1 gives 15 R1. So they just replace this K by 15, but I'm just giving an example and you place it at 1 comma 1. So 1 comma 1 we have K 0 1 0 0 0 1. So this will be our elementary matrix. Now, when we talk of inverse, first let's understand what is inverse. Right now, you are not focusing on what inverse really is. So, inverse is really like Control Z. When you press Control Z in your computer, what happens? Roll back, right? So, if we want this to roll back to its original form, what do we have to do? If I say I have to get back 1 from K and I have to get X, what is my X? 1 by K. So replace this K by 1 by K. And this will be our inverse. Simple. Let's move forward. Case 3. Case 3 says Ri minus Krj or Ri plus Krj. That's the same thing. Now let's say we perform an operation R1 gives R1 minus 2R3. So here the trick is see the RHS, see the first row and the second row, that will be your coordinates, and your scalar will come as it is as K. And like you did in case 2, similarly, first make a fresh identity. This should always be a first step. Then at 1 comma 3, where is 1 comma 3? 1 comma 3. We place minus 2. See? But here, one thing to notice, your diagonal is retained. If your diagonal is not retained, the matrix will collapse. If not right now, in future. Now, when we say about inverse, inverse is control Z. Minus 2 plus x is equal to 0. We want it to be replaced by 0 to get back the identity matrix. So your x will be 2. So your elementary matrix will be 1, 0, 2, 0, 1, 0, 0, 0, 1. Now, another thing to note. This was the first case. Let's say we had an operation R1 gives R1 plus 2R3. So your matrix will be 1, 0, 2, 0, 1, 0, 0, 0, 1. Now what will you do? How will you get it? So 2 plus x is equal to 0. I'm doing this calculation because it's the first time, but then you have to do it in your mind. So x will be minus 2. So your elementary matrix will be 1, 0, minus 2, 0, 1, 0, 0, 0, 1. This will be your E inverse. Another thing here also, this will be E inverse. Always remember, E inverse is your control Z. Next, we have done, now we have, when we have studied about elementary operations, elementary matrix, now we'll come on its application. So let's start with the first application, that is inverse of a matrix using elementary operations. Till now we were handling the basics of matrices. Now comes the major topics of matrix computations. So let's say A is a matrix and B is its inverse. This is the matrix and this is its inverse. So what do you think? AB will be equal to identity? Yes or no? Now, let's say, so this is a basic property of a matrix. Now, when we apply a chain of operations, like let we apply operation O1 to your A, what do we get? We get an elementary matrix E1. Yes, is that right? Let's say when you apply O2, operation 2, what do you yield? You yield elementary matrix 2 with respect to elementary matrix 1. This will continue until your A, that is your matrix, becomes a identity. So let's say E2, E1 of A is equal to identity. So each elementary row operation is basically corresponding to an elementary matrix like E1, E2, and so on. So now after this, We know this multiplied by this gives your identity. So we let this part as B. So we can say that B into A is equal to your identity, or B is equal to A inverse. What is your A here? A is basically, A inverse is basically EK minus 1, so on till E2 and E1. This is basically, if you take it that side, it will be B inverse. A is equal to B inverse or B is equal to A inverse. So basically, inverse of a square matrix is the product of elementary matrices that reduce A to the identity matrix. Reducing A to the identity. So we have written these steps. Similarly, if you want to write in terms of A, we can write A is equal to B inverse and A is equal to EK minus 1, E2, E1 inverse. So we'll have E1 inverse, E2 inverse, so on till EK minus 1 inverse and EK inverse. So this is representation of a matrix using elementary operations. Matrix using elementary operations. Elementary matrices, sorry. And earlier what we had seen was representation of inverse using elementary matrices. I hope this is clear. If this is clear, we'll move forward with a question. In the question, we are saying find the inverse to a matrix A and express A as a product of elementary matrices. So the question is A is equal to 1, 2, 2, 0, 1, 4, 0, 0, 1. So I hope you had seen the question in the previous slide. Now we'll solve that question. So let's say the matrix we had written there was 0, 1, 4, 0, 0, 1. Understand now what we will be doing. We'll be applying operations to make this identity. Step 1, we are considering a identity matrix I of the same order as your A matrix, 3 cross 3. We'll write that 1, 0, 0, 0, 1, 0, 0, 0, 1. Now apply the elementary row operations on the given matrix that moves towards a identity matrix. So what do you think? The first operation that we'll apply will be R3 gives R3. Let's do with R2. So R2 gives R2 minus 4R3. In this case, you'll get your A as 1, 2, 2. This will be 0, 1, 0. This will be 0, 0, 1. Right? So in that case, your E1, how will you construct your elementary matrix? I told you, you have to do it from the operation itself. What are the coordinates? 2, 3. K is minus 4. So 2, 3, we'll see 1, 0, 0, 0, 1, minus 4, 0, 0, 1. Next operation we'll apply is R1 gives R1 minus 2R2. Okay. So when we apply this, you'll get it as 1, 0, 2, 0, 1, 0, 0, 0, 1. So at 1, comma 2, you have to place -1. So your elementary matrix 2 will not continue from E1. It will be a fresh identity matrix. 1, -2, 0, 0, 1, 0, 0, 0, 1. Similarly, your now third operation, we have to make this 2 also as 0. So we have to target this using the third row. So this will become your identity now. What will be your E3? Your E3, I'm writing it directly now. I hope you understand the concept. 1, 0, -2, 0, 1, 0, 0, 0, 1. If we talk about now the inverse, we had done the formula A inverse is equal to E3 into E2 into E1. Similarly, if there would be more matrices, you could have written E4, E3, E2, 1 similarly. So now when you multiply them, you will get your A inverse as 1 -2, 6, 0, 1 -4, 0, 0, 1. This is your final answer. So this is how you solve this question. Now, if I say express them as product of elementary matrices, express as product of elementary matrices. So how will you do that? For that, you have got your E1, E2, and E3. Let's take their inverse. I had told you how to calculate. Inverse is Control Z. -4 was replaced at 2, 3. So plus 4. So 1, 0, 0, 0, 1, 4, 0, 0, 1. Next, E2 inverse. 1, 2 was replaced, 0 was replaced by -2. Now, to make it 0, we'll add plus 2. Control Z of this -2 will be plus 2 to get your identity back. In matrices, your identity needs to be with you. You cannot give your identity to anyone. If you're giving while taking the inverse, you have to control Z, means you have to take it back. So 0, 1, 0, 2, 0, 1, 0, 0, 0, 1. So now your A will be equal to E1 inverse, E2 inverse, E3 inverse. So I hope you will be able to multiply them. I'll write there. You will be able to multiply. I'll just write the matrices. You had to express them as a product. So if you not multiply, you can confirm your answer by multiplying. There's no harm in that. But this is your final answer. 0, 1, 0, 0, 0, 1. This is your answer. So this was one formula and this was one formula. The difference in the questions were you had to find inverse using inverse of matrix. And here you had to express it as a product of your elementary matrices. I hope this is clear. Now coming to your last topic of this lecture, this is the most important topic. Mostly examiners prefer this topic because this topic involves partitioning. This can be a 5 marker also depending on the complexity of the question. So let's see what a submatrix is. A matrix obtained by deleting some rows or columns. Delete some either row or column or both, you can say, is called a submatrix. But a submatrix was a base. What we'll be studying will be a partition matrix, partition matrix, or a block matrix. So basically, a matrix is said to be partitioned if it's divided into a submatrix by horizontal and vertical lines between your rows and columns. It can be partitioned in a number of ways depending on the choice how you place your horizontal and vertical line. Then let's take an example. So let's suppose you have a matrix 1, 2, 4, 9, 0, 2, 5, 7, 1, 0, 5, 6, 3, 5, 8, 3. So how can you partition this? We'll explain it using a pointer. I hope you are able to see the pointer. So the first partition is 1, 2. Are you able to see the partition? I don't think so. Let's see. 1, 2. So I hope now it will be visible. So E, B, C, D. E is represented by a small 2 cross 2 matrix, that is 1, 2, 0, 2. Let's see another combination. That's why I used the black pen for writing these topics because I needed color pens for understanding, making you understand the concept of partition. This is another partition where you see the obtained matrices are a square matrix at the diagonals. One, and then we'll take green to make the last. Oh, it's red. So this is your third partitioning. So there could be two more than one way also of partitioning your matrix. This was just for your understanding. This was not a question, but I wanted you to understand how we can partition our matrix. Now, how to divide it in a judicious way. So let's say we have two matrices A and B, and they need to be multiplied to get a product. Because ultimately you will get a question only. You'll not get your partition. That is simple thing. So let's say you have a matrix, similar matrix like these, A and B. You divided or partitioned them, and you get A as E, B, C, D, like we got here, and B you get as X, Y, Z, and U. Now, how will you obtain the product AB? I hope it is visible. I'll write it with the black pen. A, B, C, D. This is an example. E2 cross 2 was 1022. So let's say if we want to get AB, what will AB be? EX plus BZ. I don't need the partitioning now. Then EY plus BU, CX plus DZ, CY plus DU. So this is your AB as a 2 cross 2 matrix. So this was a random example that we did. This is the basic concept of how you will be calculating. But Let's understand with the help of a question. Let's say you have to find AB, where A is given to you as 31020003003001000. B is given as 21000 -1 10000 01001. Let's partition them. For this question, I'll give you the partition matrix. So one is this partitioning this. The second one says like this. So now in this case, what you'll do is you have one matrix that is A, B, C, D, E, F. And here you have G, H, I, J. This is a 3-row, 2-column, and this is a 2-row, 2-column. That is, you'll obtain a 3 cross 2 matrix as a result. So this will be similar to how we calculated for 2 cross 2 multiplied by 2 cross 2. The difference will be now this will be first multiplied with this part plus this 0 0 will be multiplied by 0 1. So this was what I was talking about. So as you can see, first A, B, C, D, E, F, G, H, I, J. To get the first element, what we'll do is we'll multiply A with G plus B into I. Similarly, for the second row, we'll get AH plus BJ. I hope this is clear. Similarly, you'll form the matrix, you'll do the multiplication and get the final answer. I hope this is clear. This is mostly solving. This can come as a potential 2 marker. Your partitioning will be of half mark. Your solving half. If you further solve it till this step and your final answer will be a half. So this is your next question. You are given A and B and you are not given the partitioning now. So you can partition on your own also. You can partition like this. Then you can also partition it like this and then solve. Why not? I hope this is clear. You partition it and then you apply similarly that we have seen earlier, A multiplied by B, and you can solve it and get the final answer. If you have any doubt in any of the question that I have done till now, you can write them in the comment section. So these are two questions that I would like you all to practice. These are two nice questions that I found which will be helpful for your examinations also. So basically, first is to partition them. So yeah, first I'll partition them like this. I'll call this A11, A12, E21, and E22. Similarly, here also you'll have B11, B12, B21, and B22. Here you need to note if you calculate C is equal to AB, this will be A11, B11 plus 0. This will be 0 plus 0. Okay. Then this will also be 0 plus 0, 0 plus E22 B2. That's all. Then the question is done. So the final answer will be, this is the final answer. You can check your answers after solving. So when we talk about the second question, now this is a difficult one where you're told to use partitioning to compute a square and a cube and then find a raised to power n. So what you do is first you partition these blocks. So I'll keep one as this, and this is a partitioning I would like to take. So because this is a block diagonal matrix, powers of A can be computed using this way also. So let's say actually these are block diagonal matrix. If you see clearly, you only have your elements on the diagonals. So if you want to calculate d square, you'll do 1 square 0 0 2 square. You'll get it as 1004. Similarly, d cube also you can calculate. You'll get it as 1008, and d raised to power n will be 1002 raised to power n. Similarly, for n also, we can do the same thing. N raised to power n cube, n square. Now, I don't know if you all may be knowing this concept or not. This n is also a standard shift matrix, which we call as a nilpotent matrix. See, in this matrix, when we calculate, let's say, n square, you'll have a shift. So this will be 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0. Now, when we see n cube, this row will go, another 0, 0, 0, 0, 0, 0 row will come, and this will be a final row. And for n raised to power n, what you'll have will be a final 0 matrix. Those who know this property will ace this 2-marker problem. But those who do not know this property, or those who do not do the partitioning well, will face difficulty surely in doing this question. So this second question is a star question. Practice these types of questions for examinations. Now moving on to the final concept based on partitioning. Inverse by partition. We have seen inverse using elementary operations. This is our control Z. Now we'll see it using partitioning. So let's say you have an A matrix B, C, E, D. This is n cross n, let's say, right? Now, in order to have a matrix, a block diagonal matrix, we would be having this in the form, this will be the order, basically. Roughly, we can say S cross S. Now, B and D, I'll write this, B and D should be a square structure. Square structure. N is equal to R plus S. Now, if I say A into inverse is equal to identity, we can say B, C, E, D And let's say A inverses X, Y, Z, B is equal to I1, 0, 0, I2. So when you solve them, you'll get Bx plus Cz, Ex plus Dz, By plus Cv, Ey plus Dv is equal to I1, 0, 0, I2. So on solving these equations, you'll get X as B inverse minus B inverse Cz, Y as minus B inverse Cv, then V as D minus E B inverse C whole inverse, and Z as minus VE B inverse. So you'll have to learn this. Either you derive it. If not deriving it, you'll have to remember them. Mostly the nomenclature is that we start with V because mostly V is known, then Z, Y, and X, then move on to A verbs. Right? So let's see a question. In this question, we have a A matrix which is 2, 0, minus 1, 5, 1, 0, 0, 1, 3. I'll partition it this way now. So B, C, E, D. Now understand, if you change the ordering of B, C, E, D, these formulas will also change. Please note, this is a very common mistake that everyone does. B, C, D, E, and your whole question is wrong. Please note. So first we'll calculate B because D is known, E is known, B inverse you can calculate, and C is also known. So when you calculate V, you V1013 minus 50. Now B is 2. How control Z? How can you get your control Z back? Control Z inverse is your. How can you get your identity back? By multiplying it by 1 by 2. 0 and minus whole inverse. So when you calculate it, you'll get it as. I'll writing the final answer to be 6 minus 5 minus 2 and 2. Similarly, you'll get Z as 5 into minus 3, 1. You'll get your X as 3, Y as minus 1, 1. So when you write E inverse X, Y, Z, V, you'll arrange it in a proper way. Minus 1, 1, minus 15, 6, minus 5, 5, minus 2, 2. So your X is 3. This is how you get your A inverse using partition. So this was all about today's lecture, but I'll leave you all with a homework question. So write down question 1. Using inverse by partitioning, what we have covered right now, I'm not writing the whole question. 2, 1, 2, 3, 3, 1, 2. I want you to use inverse by partitioning to find its inverse and then confirm that A into A inverse is equal to the identity. This is your first question. Then your second question is use find the inverse of the matrix using partition method. The A is 1, 1, 1, 4, 3, minus 1, 3, 5, 3. I hope so that you will be able to solve these questions. These are based on just the previous topic that we have covered today. If you want, I can give you the answers. The answers to the first one will be It was 1 by 10, 14, 2 minus 4, minus 15, 0, 5, 11, minus 2, and minus 1. Here, your A inverse will be 1 by 18, 1, 7, minus 5, minus 5, 1, 7, 7 minus 5, and 1. These are your answers just to compare. And after solving both of these questions, you can check your answers. If there is any discrepancy in the answer, you can write them in the comment section and I'll check and rectify them in the next video. And after questions like these, you have to write hence verified. Otherwise, minus half could be deducted because we don't know where it is verified. So thank you. I hope you like this lecture after 2 months. If you like the video, do like, share, comment, and subscribe to my YouTube channel. And I will be posting your second lecture in a while. Till then, practice these topics because these topics will serve as your base to your upcoming topics. We'll be covering direct method. We'll be doing linear system of equations first of all, then we'll be seeing some direct methods and then some indirect methods. We'll be seeing decomposition algorithm, triangular decomposition, LU decomposition. So there's many topic to go, but this was just a gist of what all we'll be doing. So thank you. Bye bye.